Imagine standing on the edge of a cosmic cliff. Behind you, the Milky Way. 400 billion stars. Everything humanity has ever known. Every civilization that might exist within it. Every world we could ever dream of reaching. And ahead of you, nothing. A void so vast that the next major galaxy, Andromeda, sits 2.5 million light-years away. Here's the terrifying part. Even if we could travel at the speed of light, the fastest anything can move in this universe, the journey would take longer than the entire existence of modern humans on Earth. So what hope do we actually have of crossing that distance? And why does physics itself seem designed to keep us trapped? Let's start with something we think we understand: distance. We've talked about interstellar travel before. Proxima Centauri, our nearest stellar neighbor, sits 4.24 light-years away. With our fastest probe, the Parker Solar Probe, it would take over 6,000 years to get there. That already feels impossible. Now zoom out. The Andromeda Galaxy isn't 4 light-years away, it's 2.5 million light-years away. That's not a bigger number, it's a different category of number, one that breaks the way our minds process scale. Let me try to make this tangible. If the distance to Proxima Centauri were a single step, the distance to Andromeda would be about 600,000 steps. That's walking from New York to Los Angeles, twice, and then some. Or think of it this way: light, moving at 300,000 kilometers per second, takes just over 4 years to reach our nearest star. That same light takes 2.5 million years to reach Andromeda. When the light we see from Andromeda tonight began its journey, our ancestors hadn't discovered fire. They hadn't developed language. They were barely distinguishable from other primates roaming the African savanna. And yet, Andromeda is considered our neighbor. It's the closest major galaxy to us. Beyond it, distances only grow more absurd. But here's where it gets worse. Even if we could somehow build a spacecraft capable of traveling at a significant fraction of light speed, we would still face a wall that no amount of engineering can overcome: the rocket equation. Every spacecraft needs fuel. That fuel has mass, and to accelerate that mass, you need more fuel, which also has mass, which requires more fuel. It's a vicious, exponential spiral that punishes any attempt at high-speed travel. To accelerate even a modest spacecraft to just 10% of light speed would require more energy than entire nations consume in a year. And that's just acceleration. Slowing down at the destination demands the same energy expenditure all over again. For interstellar distances, this is already a near insurmountable problem. For intergalactic distances, it's not a problem. It's a wall, an absolute barrier. The energy required to accelerate a spacecraft to speeds that would make an intergalactic journey possible in any reasonable time frame exceeds the total energy output of stars. We're not talking about technological limitations that future generations might overcome. We're talking about the fundamental economics of physics. And the rocket equation doesn't care about your ambitions. Now you might be thinking, what about other propulsion systems? What about nuclear drives, ion thrusters, or even more exotic concepts? Let's walk through them. Ion thrusters are remarkably efficient. They accelerate charged particles using electric fields and can operate continuously for months or even years. NASA's Dawn probe demonstrated their effectiveness beautifully. But here's the catch. Ion thrusters produce extremely low thrust. They're excellent for gradual acceleration over long periods within our solar system. For an intergalactic journey, that low thrust means centuries just to reach cruising speed. And cruising speed, even after all that time, would still be a tiny fraction of what we'd need. Nuclear thermal propulsion is more powerful. A reactor heats hydrogen to extreme temperatures, generating significant thrust. It's roughly twice as efficient as chemical rockets. But twice as efficient still isn't remotely enough. We're not dealing with a problem that can be solved by doubling efficiency. The energy requirements scale with the square of the velocity. To cut travel time by half, you need 4 times the energy. The math is brutal. Nuclear electric systems go further still. combining reactor power with ion technology. More efficient, more sophisticated. Still nowhere close. The deeper problem is that all these systems are incremental improvements on fundamentally limited approaches. They make interplanetary travel more feasible. They might eventually enable interstellar missions across decades or centuries. But intergalactic travel? The numbers simply don't work. What about generation ships? This is often proposed as a solution for interstellar travel. Massive vessels, essentially self-contained worlds, where generations of humans would live, reproduce, and die during an epic voyage. The original crew would never reach the destination. Their distant descendants would. For a journey to Proxima Centauri, this might theoretically work. Several thousand years. Difficult, but conceivable if we could solve the engineering challenges. But Andromeda? Think about what we're actually proposing. A journey lasting 2.5 million years. That's not generations. That's geological time. That's the time it took for humans to evolve from our earliest hominid ancestors. A generation ship traveling to Andromeda would need to sustain a viable population for longer than our species has existed. The social challenges alone are staggering. How do you maintain a functioning society for millions of years? How do you preserve knowledge across 100,000 generations? How do you prevent catastrophic social breakdown, civil war, or simply the gradual drift of purpose over timescales that make human history look like a footnote? Every empire humanity has ever built has collapsed within a few thousand years at most. We're asking a single vessel, isolated in the void, to maintain coherent civilization for 1,000 times longer than any society has ever survived. And that's assuming the ship itself doesn't fail. No machine humanity has ever built has operated for more than a few decades without major maintenance. We're proposing a vessel that would need to function flawlessly for millions of years. Every seal, every circuit, every recycling system, all of it would need to work perfectly for longer than mountains stand. The concept isn't just impractical, it's a category error. We're applying solutions designed for human timescales to problems that exist on cosmic timescales. Let's pause for a moment and really absorb what we're up against. The Andromeda Galaxy is 2.5 million light-years away. Even traveling at 99% of light speed, an impossible feat with any technology we can imagine, the journey would take approximately 2.5 million years from an outside observer's perspective. Special relativity does offer one strange consolation. For travelers moving at such speeds, time dilation would compress their experience. From their perspective, the journey might feel like decades rather than millennia. But this raises its own impossible problems. No life support system could sustain a crew for decades in the hostile environment of intergalactic space. No spacecraft could shield its occupants from the cumulative effects of cosmic radiation over such periods. The human body, as we've discussed before, isn't built for extended spaceflight. Bones weaken, muscles atrophy, hearts shrink, eyes deteriorate, and that's just for trips of a few years. A decades-long journey through the void between galaxies, far from any star or planet, without any possibility of resupply or rescue. This isn't a challenge. It's a death sentence with extra steps. But the problems don't stop there. Intergalactic space isn't empty. That's one of the most persistent misconceptions. Between galaxies lies a sparse but real medium of gas, dust, and particles. At the speeds required for any meaningful intergalactic transit, even the tiniest fragment becomes catastrophic. A particle no larger than a grain of sand, striking a spacecraft moving at even 10% of light speed, would impact with the energy of a small bomb. At higher velocities, the destructive potential scales exponentially. Shielding against such impacts would require mass, enormous amounts of mass. Which brings us back to the fuel problem. More mass means more fuel. More fuel means more mass. The cycle repeats, and the numbers become impossible. Navigation presents another fundamental obstacle. In interstellar space, we can at least use distant stars as reference points. In the void between galaxies, even those reference